Okay, so we've talked about security metrics thus far. We have been focusing on a continuous loss distribution, where we're essentially trying to compare the expected loss when you invest in security and when you don't. The presentation thus far has been very general. It's if you can supply a reliable loss distribution function for different security investment levels, then it would work great. But in practice, it can be very hard to come up with a credible continuous loss distribution function that actually is empirically validated. So, furthermore, they can be very hard to analyze if you're thinking about general functions. So, we can instead greatly simplify our model down to essentially the most fundamental concepts we need. And here's the simplified scenario. Okay, rather than having a range of possible outcomes where you lose at differing levels, you only have two outcomes: 0 and a loss of lambda. If that loss of lambda is going to be greater than 0, it's a fixed loss, and it's going, rather than occurring with a full probability distribution, because this is the only loss that can occur, you only need a point estimate for what that probability of suffering the loss is. And so we're going to say PS is the probability of a loss at that time, at that loss level, excuse me. So we can, if PS is the probability of a loss if you invest with the security level S, then that means, because we only have two outcomes, with probability 1 minus PS, then you suffer no loss at all. So if you make these simplifying assumptions, these are called a Bernoulli loss assumption, this can greatly collapse down the metrics that we saw previously. So annual loss expectancy becomes just the probability of a loss at security level S times that loss amount. The expected benefit of security just becomes the difference in probabilities between of suffering a loss with no investment in security to an investment at level S. And expected net benefit of security just becomes the expected benefit minus security level S. So this greatly simplifies things, and in fact, it nicely maps on to some of the examples we've already seen. So if we go back to the antivirus example we've talked about, where you suppose that someone could suffer a hack and that would cost $2,000, antivirus costs $75. If we slightly tweak the probabilities here to say without antivirus there's a 10% chance of being hacked, and with antivirus there's a 1% chance, well, if you just go through and do your expected utility calculations, you could end up with a table like this we saw previously. But you can also frame that in terms of the variables under Bernoulli loss assumptions. So the minus $200 for what you lose for not buying antivirus, well, that's your expected loss with no security. Whereas the loss of $95 is the expected loss with at security level S minus the money spent to reach security level S. The 0.1 probability of not buying antivirus but getting hacked is P0. The 1% probability of being hacked if you do buy AV is PS. The $2,000 loss is lambda, and the $75 you're out for the AV is just the security level S. Again, this is assuming that you have the effective security assumption where S is equal to C. Again, here are greatly simplified metrics under the Bernoulli loss assumption. And if that's not simple enough for you, we can make one final simplifying assumption, which is that you can normalize the loss to rather just being a general loss lambda. It can be just normalized to 1. So if you do that, you eliminate that variable, and you end up with just a metric where you're essentially calculating probability differences and security spending. And that's all we'll talk about for now.